Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 47, we will cover deep learning. So, the different concepts that we will cover will be the basics of deep learning architecture, optimization challenges and algorithms used in deep learning categories, and then finally we will learn deep learning with an example in Python. So, deep learning is a subset of machine learning based on deep multi-layered neural networks. We have already discussed this in the previous lecture. So, over here you can see that instead of 1 or 2 layers, we have got many more layers, right, which means that we will be able to do more abstraction, right, that means more intelligence, we can extract more features, right. So, so deep learning is basically a neural network with many layers. So, this multiple what happens is, because there are so many layers and so many connections, and we are the way the process remains same as we in artificial neural networks of finding the setting the weights in the forward pass and then coming to the output, then going in the backward propagation. That means in the backward pass we try to adjust those particular weights and all, so that the loss reduces, and for that we use have a loss function, and we use optimization to find out in which way we should find out the best possible solutions for those weights and biases, right. So, multiple hidden layers automatically learn hierarchical representations of data that we have discussed earlier. That means the initial layers may be focusing on the more basic stuff, like for example, if it's an image, it will look into edges and from pixel it will look into the edges in those pixels by combining those pixels, and then in the upper layers it will try to find some shapes and then sub objects or objects, right, and in that way it progresses, right. So, models automatically extract features from raw inputs. We don't have to do any sort of feature engineering. Images, audio, text, sensors, all these things could be fed, and we can extract features from that, and model learns directly from that. And unlike traditional machine learning, feature engineering is not required in deep learning. But data requirement is obviously much more compared to other machine learning models. Model complexity is also very high, and the compute requirement requires actually GPUs and TPUs. That means normal CPUs will not be able to handle this kind of load, and we have to go for these GPUs and TPUs, right. So, the structure looks like this. There is an input, then in the hidden layer 1, low level things are extracted, edges for images, frequencies for audio, tokens for text, those are extracted, and those are understood. Then in the hidden layer 2, in the mid level, the shapes for images, phenomes for audio, phrases from tokens, those are formed. And then in hidden layer 3, which is a little bit higher level, we find the objects from shapes, then semantics from phenomes, and then intent or meaning from these phrases, right, what exactly is being understood, and then from there we can do output prediction. So, you see all these large language models, these also follow the same architecture, right. It is one type of this deep learning is using the transformer architecture. We can go for finding what should be the next word that should be predicted, right. So, that is a large language model. So, if it's like if we are going for images and all, and to extract meaning out of those images, like from a video we want to extract the vehicle, or even the vehicle is moving that we want to extract, then we use CNN, those kind of deep learning architectures. So, there are several deep learning architectures which could be utilized. So, this approach is known as the representational learning. That means model automatically discovers useful features. So, in general deep learning architecture, each hidden layer transforms the input representation into a higher level feature space. So, that means we are increasing the number of features, right. And deep learning network with L layers could be represented like this, and where HL is the representation at layer L, WL is the weight matrix, BL is bias, F is the nonlinear activation function. So for example, if I have got around three layers, then you can see that the first one is this one, and the second one is this one, and the third one is this one, and the fourth one is where we are actually doing the prediction, right? So that the first one is the input features, the second one is hidden layer 1, this is hidden layer 2, and then in hidden layer 3 we are finally getting the output. This is Y. So from X we are predicting Y, but in between we are creating so many other features. We are converting this entire thing into a much higher level feature space. So the hierarchy of edges, shapes and objects emerges automatically during training as deep neural networks learn progressively more abstract representations of data. So this is why it's a black box model, right? How this is happening, of course, why it is happening, this is difficult to explain. So usually we have seen that at the initial hidden level, basic features are coming out like edges and all, but in higher levels we can increasingly, because we are getting the information from the previous layers, we can increasingly form more complex features and so on. So this is actually represented, these functions could be represented like this, because it's a series of activation functions F4, F3, F2, F1, which is even starting from X, and then the result of this one would be acted upon by F2, and the result of this one would be acted upon by F3. So this that helps in back propagation. If you remember that calculus rule that when we applied partial derivative, we have used that this kind of a function, and then we can solve the entire thing together by taking partial derivative, right? So to generalize this Y equal to FL, because there could be many n number of hidden layers, FL into FL minus 1 and so on. Eventually the most inner layer is F1x. So this composition of functions allow deep networks to model very complex nonlinear relationships. So activation functions remain same, ReLU, sigmoid, softmax, these are the different activation functions. Loss functions remain same as artificial neural networks, mean squared error, cross entropy loss. Back propagation is same, forward pass, backward pass, both has to happen, and then this optimization algorithm becomes very, very important in this case, right? So we can use gradient descent, Adam optimizer, then there are several other approaches as well. Now why optimization is important? This is because deep learning is basically, we are dealing with billions or millions or billions of parameters, right? And so many weights, and we are dealing with huge amounts of weights and biases, right? So optimization in deep learning refers to the process of adjusting these weights and biases to minimize the loss function, thereby improving prediction accuracy. Now because there are billions and millions of parameters which needs to be adjusted, so we require efficient optimization methods. So optimization becomes very important, otherwise the processing time would be too large, right? So training deep networks is fundamentally a high dimensional nonlinear optimization problem. So we need to understand about how the losses, how the loss changes, or what is the loss landscape, right? So loss surfaces are very complex because there are so many layers, and there is nonlinear activation functions, multiple layers, millions of parameters. The loss surface is very, very difficult. It's not like that in one direction, if I change the parameters, everything changes. So sometimes it changes, sometimes it becomes flat, then again it starts changing. So it's not that simple. So it contains local minima, saddle points, flat plateaus and sharp minima, which needs to be overcome to reach to the final solution, right? So one of the most common optimization techniques is the gradient based optimization. There are different variants of it, like batch gradient descent, stochastic gradient descent, mini batch gradient descent, depending on the same gradient descent approach, but with different varieties. You can do this using smaller batches and so on. So that is where mini gradient descent is. You take a bunch of parameters, features, and then you work for those. You use the gradient descent. Then you take the other batches and so on. So instead of taking all together, so these are the different techniques that are there. So most deep learning models are trained using gradient descent algorithms. Gradients of the loss function with respect to the model parameters are computed using back propagation, which we have learnt earlier, so dl by dw, So dl is the loss function and dw is the weights, right? For that means we are changing the model parameters. With respect to the model parameters, we are finding the gradient of the loss function. That is how the loss is changing. And the network weights are iteratively updated using gradient descent to minimize the prediction error. So we will probably try to move the weights in those directions where the gradient descent is higher. So the update rule is wt t plus 1, which is the predicted, which is the new weight, where wt is the current weight and eta is the learning rate, and this gradient and this is the gradient loss of base in respect to those particular weights that we are considering. So this is the gradient of the loss function. So this is represented like this. So then what happens is that means even though when we are using this sort of optimization problems, it can result in some local minima. So in the loss landscape, if I take a 2D graph of it, so actually it's not a 2D graph, it's not even a 3D graph, because depending on the features, it's a very complex graph, complex surface, right? So, but to make it easy to understand, we have taken a 2D graph. So here you can see that the loss function value is changing. So it seems like this here, after that it is actually increasing. So this is a local minima. But actually if I keep on changing the parameters, we see again it starts reducing, and then we finally reach the global minima. So but if I stop here, I will stuck with this value, right? So I am actually wrongly predicting the weights. So that is the local minima problem. So so local minimum is a point where the loss is lower than nearby points, but not necessarily it's the global minimum, right? And it is less, it's not equal to the global minimum. And gradient descent may stop prematurely and model may converge to suboptimal solution. So we find that the gradient is 0, that is there is no change. But it's a local minimum. So this can be mitigated using stochastic optimization methods such as mini batch gradient descent that we were talking about earlier. Then advanced optimizers such as momentum and ADAM. So in the last lecture we have used ADAM, and then proper weight initialization and techniques such as ReLU activation and batch normalization. So this we will learn subsequently. Now what is the momentum algorithm? So the momentum algorithm accelerates learning by adding a new term in addition to this to the gradient descent approach, right, which is the velocity term. So which actually contains information about the past gradients, right? So this results in smoother updates and quicker convergence. So this is given by this equation Vt equal to this gamma Vt minus 1 plus eta the gradient loss as per the particular weights. So this gradient of the loss function at current weights, and Wt is the current weight and Wt plus 1 is the updated weight. With that means Wt plus 1 is Wt minus Vt. So now what is happening is the weight is updated by moving in the direction of the accumulated velocity, which incorporates information from past gradients. So that is what is happening over here. So that means past gradient, the gradient value is also reserved, is also considered. It's not the current gradient only. So that's why, because we are also considering what was there in the past gradient, so automatically sometimes we can overcome this local minima and so on. Then this is the ADAM optimizer. So this is another algorithm which we can use for optimization. It combines not only momentum, it also uses adaptive learning rates and gradient descent, which results in faster convergence and stable training. So there is this is the the weight update rule, whereas this is the first moment estimate and this is the second moment estimate, which is for the adaptive learning rate, and the first estimate is for the momentum part, which we just saw earlier. So the momentum equation calculates the exponentially weighted average of past gradients, which smooths the gradient updates and prevents oscillation. That means if the value is increasing, we will keep on moving in that direction. If it is decreasing, then we can also that sudden oscillations could be normalized to or it could be prevented to a certain extent. The next equation, that means this adaptive learning rate tracks the variance of gradients and adjusts the learning rate for each parameter individually. And weight is updated using both the momentum MT and the adaptive scaling from Vt. So this Vt is the moving average of squared gradients. So and then B2 is the decay rate for squared gradients, and so this is where we are actually trying to see that we are looking into the variance of the gradients, and not only the value of the gradients from earlier iterations, but also the variance of the gradients is also considered. Then this is the problem of vanishing gradients that we talked earlier. So as you can see over here, as we are back propagating from output to layer 3 to layer 2 to layer 1, the slope is gradually decreasing, right? So that means the gradient is gradually vanishing. Now this occurs in deep learning when gradients become extremely small during backpropagation, causing early network layers to stop learning and hindering deep model training. So this is shallow training is happening, right? Because for deep training we have to reach till this part, but the model cannot reach there because there is no gradient loss and the optimization stops there, right? So gradient descent may stop prematurely and model may converge to suboptimal solutions. So this is very common for sigmoid and tanh activation functions, but if you use ReLU activation or batch normalization, then this problem doesn't occur. Then there is the question of the problem of exploding gradients. So over here what is happening during the forward propagation, the gradients of the network's cost function grow exponentially during the training phase, and extremely large gradient values can cause this is not during this is also during back propagation. So extremely large gradient values can cause large updates to the weights, and the weights can become not NaN or infinity, leading to numerical instability, right? So both it can become very less or it can very high. So we need to take some steps so that this doesn't repeats. So two of those steps that we can two of those approaches that we can adopt is weight initialization and batch normalization, which actually stabilizes the signal and the gradient flow to a certain extent. So stabilizing the signal means the information that is passed between the layers, that becomes stabilized, right? So that means there are no sudden changes. So sometimes we can do it by normalization, and the gradient flow also becomes much more smoother. So the first technique is weight initialization, where this sets the initial, where using this technique we can set the initial random values for the neural network weights, which is very crucial for preventing the exploding or vanishing gradients and enabling convergence. So if the initial weights are given judiciously, then this problem of this vanishing gradient or this exploding gradient will not happen. But initial things are we usually do it in a random way, but there are some techniques to find out. Instead of finding the weights in a random way, we can use techniques such as Xavier for sigmoid and tanh, and HE initialization for ReLU to maintain stable activation variances across layers, avoiding the symmetry problem of zero initialization and accelerating training speed. So that means it maintains stable activation variances across the different layers, right? So that actually avoids the that means the gradually reducing between the layers, the gradient starts reducing. That will not happen. Now the other approach is the weight normalization. So batch normalization, the batch normalization. So this normalizes the inputs of each layer during training to stabilize learning and improve convergence. Now what it does, it standardizes the activations within a mini batch, not the full thing. It takes smaller groups of features by computing the batch mean and variance and then normalizing the values to a common scale. So that actually to a certain extent standardizes the activations within this particular batch. And after normalization, batch normalization uses learnable scaling of gamma and shifting beta parameters so that network can adopt the normalized activations while maintaining stable training. So this is whenever we are the learning parameter, that how much the shift would be, that is how much change of that gradient, change of the parameter weight should happen. So those we can done in a more better way. So there are different types of deep learning models. We have discussed this earlier, that is MLP, which is a very basic deep learning where it's almost similar to ANN, but instead of 1 or 2 layers, we have got much more. We can have 2, 3 or more layers, and it's a general purpose deep network used for structured data. whereas for we can go for this is MLP. You can see we are just having different hidden layers, and then we can use same activation functions, and then we are getting the final outputs, right. So these are the predictions. And then then for CNN, this convolution neural networks uses this could be used for spatial data like videos and so on. Those we can identify certain features and all. So CNNs learn where patterns occur, and then RNN or recurrent neural networks used for sequential or temporal data. So RNN learns when pattern occurs, and then there are the transformer networks where it's used for large scale AI applications such as language models, intelligent transportation systems, and so on. Now coming to an example, so we are trying to predict urban heat island intensity, and this is given as the temperature difference. So this is the target variable, and we are hypothesizing that building density, vegetable NDVI, and road surface. Building density is the total amount of built up area, which ranges from 0 to 1. Then vegetable index representing green cover, it is also between 0 to 1. So that is how much green cover is there in that area, and total amount of road surface, because we know that if green cover is less, road surface is more, built up area is more, usually it ends up with larger temperatures, right, higher temperatures. So it results in formation of heat islands. So we start as earlier, import numpy as NP, import pandas as PD, matplotlib.pyplot as plot, then sklearn model selection, train test split, then standard scaler. So this part is pretty standard. Then all the different metrics, R square, score, mean squared error, all these things we can get also. Then we are importing this axis 3D plot, because we want to design some new kind of plots, because we wanted to understand the loss surfaces and all. And then comes the TensorFlow models, right. So TensorFlow already we have discussed that it's one of the tools, it is one of the libraries that is available for specialized deep learning models, and we are importing that as TF. And tensorflow.keras.models import sequential. So sequential model helps build neural networks by stacking layers one after another. So it's basically a standard neural deep learning network model. And then from TensorFlow keras.layers import dense batch normalization. This is where dense layer for fully connected neural network layers, and batch normalization for stabilizing training by normalizing layer inputs. So we already have we understand what is batch normalization, right. So that also we have to import. And then finally we have to also think about the initialization as well. So from TensorFlow we also import GLOROT uniform, which is nothing but Xavier initialization, where it's a weight initialization method that helps maintain stable signal flow in deep networks. We just discussed about that in the previous slide. So we are loading the dataset uhi_dataset.csv. We are storing it in the data frame, and then we are printing the DFF, printing the head and the columns. So you can see the first 5 rows of the data and the column values. These are first printed, and then after that rest is standard. We declare what is X and what is Y, what is being predicted and what are the features, and then we do the train test split, and we keep the test size as 20% of the data, and random state is kept at 42. And then we run the standard scaler, and we transform the train and the test data using the standard scaler function, right. So after that we define the model first. So the model is going to be sequential. That means we are first declaring how many neurons should be there in the different layers and how many layers should be there. So dense 32 activation ReLU, kernel initialization is GLOROT uniform, input shape is equal to 3. So this is the input features. We are starting with 3 features, right. And then activation function is ReLU, and this we are using this this weight initialization using this GLOROT uniform function, right. And then batch normalization happens after after each step we do batch normalization, and then the data moves to the next layer, or rather next the signal moves to the next hidden layer. So then the next layer is where, so in the first one we have got 32 neurons, and batch normalization normalizes the outputs of the previous layer to stabilize training and improve convergence, which we have learnt earlier. And in the second layer there is 16 neurons, and in the third layer there is 8 neurons, right? And finally we have the final layer, which is 1 neuron, which is the final output layer, and we can predict the continuous target variable, which is UHI intensity. So this is that's why there is a single neuron over here. So the next job is to compile the model. We are still not run the model, we are still organizing the model. So optimizer in this case would be the Adam optimizer. So the learning rate is set as 0.01. The loss function is MSE. Along with that, we are also using MAE as well as an additional metric. So Adam optimization algorithm updates the network weights using a learning rate of 0.01, and the mean squared error is the loss function to measure the prediction errors, and the mean absolute error is an additional evaluation metric used to monitor model performance during training. Now MA is basically the average absolute difference between predicted and actual values. So then we do we fit the model.fit, x train and y train is the output and the input, the features and the prediction, the thing the prediction is both given here. The validation speed is 0.2, that is we keep 20% for validation. The total number of iterations that we will go through is 100, and batch size is 32. That means we go for mini batches of 32 samples, updating weights after each batch, and then it is going to be verbose equal to 1, which means that you can see for each iteration you can see the steps, right? So I have not given the steps output over here, but in the last ANN lecture you have seen already that how this verbose output comes. So then we are predicting we are predicting for the test data, and once we are doing that, then we can from there we can get the R squared score, and we are also getting the mean squared error value as well, right? For both y test and y pred using the y test and y predicted data. So once we do that, we can plot this. We are printing the R square value, which is 0.9, RMSE value, which is 0.24, and then we are plotting the training loss. That is at each epoch. That means in this direction, this 100 epochs are there. In each epoch, what is the loss in the what is the training loss? That means how and then not only the training loss, what is the validation loss, right? So that means with the validation data set, how the values are changing, and with the training data set, how the values are changing. So you see that this is how the loss function this is reducing by each iteration of the changing of the weights, right? So eventually you see there is no further change. Now if we see that the validation is becoming more flatter, whereas the training is more solid, in that case we can see that there is no there is a lot of instability in the prediction, right? But here it is more or less stable. So the training validation loss plot shows whether the network is learning and if convergence is stable and if overfitting starts. So overfitting is when you will see that the prediction for the predicted data is actually is more flatter, right? In that case, the training is more flatter. So in that case, we will see if there is overfitting or not. So and the prediction is not that good in that case. So that is what we are doing over here. So this is the plot, and then next we are plotting the predicted versus actual over here. So we are seeing that actual UHI intensity that is being that is there, and the predicted UHI intensity we are plotting that, and then you can see the values of that particular scatter plot, which shows that the prediction model is working pretty good. So this is where we are looking into we have given you code for doing the loss function, or to actually plot the loss landscape. But actually this is not true. Why? Because the number of features for which we are the loss landscape is basically depends on all the features that we are adjusting weights for, right? But the problem is we cannot visualize that, right? Because there are maybe thousands of features that we are the weights for which has been changed. But so what we do is instead of taking all the features, we take a couple of features, right? And then we will use it to determine the loss surface based on the actual the learning function that we have used, right? So a full DNN has too many parameters to visualize directly. So this code, this particular code that we have given, plots a two-weight slice of the loss surface around the learned solution. So whatever is learned, so we already know that how the values of the loss function is reduced. So for that solution, for the values of this two, how the weights for that two-weight slice of the loss surface is actually taken, and then we are able to explain, with that we are trying to explain the local minima, flat areas, smooth steep regions, and the overall optimization difficulty that has been encountered. So this actually shows the loss surface. In this case, we have not seen too much of a complexity over here. And another way to represent the same loss landscape is to use a contour plot where you can see that these are contours of different colors or shade is given, and the actual solution is given over here, which is the the final value, right? So this is the code for that, and the learned solution is actually given in over here in red. And this code again plots the two-weight slice of the loss surface around the learned solution, and this helps explain local minima and all the same things that we did earlier. But instead of a 3D surface, it shows the contour lines like a topographic map, where each color represents a different loss value, and we can that means for each for different kinds of losses we are getting different value, different colors, and it shows that how we have arrived at the final the value of the loss, the final loss function, right? The value of the loss, final loss value. So these are the two plots which sometimes it's not important to generate them, but it actually helps us in understanding how we have found how the overall loss landscape is, that is how the loss value has changed as along the way of the these weights have been gradually changed, and how the loss value has eventually changed, and we have reached a point where the loss value cannot reduce further. So that is why this actually helps us to visualize that, but it is not that important. For this is optional, whereas till the prediction part, and you can see that how the loss function, earlier we have shown you that how this particular the MSE value has changed over the different epochs. That actually tells you that is the model predicting properly if there is overfitting or if there is convergence and so on. So this is how we develop deep learning models. So these are some of the references you can use. And to conclude, deep learning extends neural networks to multiple layers that automatically learn hierarchical representations of complex data, enabling powerful predictive models when combined with efficient optimization, proper initialization, and large-scale computational resources. Thank you.